Welcome to Module 45, or Modern CNNs, ResNets and beyond. So, two caveats. I think the first caveat is that most of this module is going to be about ResNets, with only a small sliver of beyond at the end of the module. And I should also mention that there have been lots of new developments in computer vision and modifications to CNNs above and beyond ResNets. So calling them modern is a bit of a mixed bag. On one hand, they're as the years pass on, they're becoming less and less modern. But on the other hand, even to this day, the day to which I'm posting this this module, they're still very commonly used in a variety of real-world settings. I myself have used them quite a bit in some real-world deployments of machine learning. So ideally, at the end of today, you'll be able to explain why very deep plain CNNs can degrade in training accuracy and how residual skip connections can address this. We'll define what a skip connection is. You'll be able to derive the residual block equation, or at least understand it, and trace gradient flow through a skip connection. Remember, we've seen gradient flow quite a bit up until this point, and we're going to just kind of revisit it within the context of this new skip connection, high level. You ought to be able to implement a residual block in PyTorch and verify that it improves training stability on a small experiment, or at least when I say verify, I mean check if it improves. I'll tell you why I have to qualify that in a moment. We're going to compare key modern CNN design patterns, so ResNet, bottleneck blocks, depth versus width versus resolution, and justify where each of these is important. So this is more or less a practical considerations of how to design CNN for deployment, and then diagnosing failure modes, including a variety of things. We're not going to see too much of this, to be honest, but it's going to be in associated materials. So one surprising failure of plain deep nets, or deep plain nets, this goes back to 2016, but the message remains that occasionally for a lot of architectures, if you keep on adding more and more layers to a plain CNN of the type we've defined in the previous module, eventually you're going to end up increasing training error, not just test error. This is a cartoon example, which I'm not sharing the code because it's a cartoon here, but the idea is that you'll end up looking something like this. You'll have a 20-layer good old-fashioned CNN with just blocks and blocks of convolutions and normalizations and activation, nonlinear activations, one block after the other. And you can have 20 of these, so relatively shallow but still quite deep, versus 56, so more than twice as deep. And then often in real-world scenarios for lots of data, you'll encounter situations where over the epochs of training, this is the training situation now, you'll see that you actually get worse as you increase the number of blocks you have. So the blue curve is a 20-layer CNN network. The dashed orange is a 56-layer CNN neural network. And often you'll see training loss will be higher for the bigger, more complicated ones. And so on one hand, we've seen something like this. We've seen situations where when you increase the capacity or the flexibility or the power of a model, you'll end up getting worse performance on testing or validation. And we call that overfitting, and it is overfitting, but this is not overfitting. So this is the performance on training. So normally when you increase more and more flexibility or capacity of a model, we've learned that you ought to do better and better on the training data. And whether or not you do well on evaluation, testing, validation is another question, but deeper models should be doing better and better on training. But the surprising thing, defined or talked about in this paper, is that it's not always the case. You can get worse performance eventually the deeper and deeper you go. And so why is this? This is a bit of a problem. So the idea goes back again to the idea of gradient flow, and so importantly, you have to understand that component of this course. But remember, we're passing gradients through the network from the end towards the beginning, towards the inputs. So you have a plain neural network with L layers of blocks. This is, again, simplifying things a little bit. We have a loss function, or an empirical risk, and we want to see what is the derivative of the empirical risk with regards to our input variables x sub 0. As we defined, again, in previous modules ago, this is going to be a product of the derivatives at one layer with regards to the others. This is because of the chain rule. We derived all of this previously. I don't want to relitigate this, but this is a product over the big L layers of your network, and it's going to be basically one transpose of these weight matrices one after the other. Okay, so we've talked a lot about this. We multiplied by the gradient of the nonlinear function, which can be sigmoid, it can be ReLU. Normally it's ReLU. We talked previously that, well, if you have the norm or the size of these weight matrices, if they're small, oh, here we go again. Let me see if I can fix this without crashing. Good. Thank goodness for Linux. Anyway, if the norms of these weight matrices are small, if they're like much smaller than 1, or if the gradients of the nonlinear activations are approximately 0, then you're going to end up with vanishing gradients, and then therefore you won't be able to adjust anything at the earlier layers. You're not going to learn anything. So layers near the input will receive near 0 gradient signals. This means that the parameters won't move. You're wasting time. You're wasting opportunity. It's not good. We introduced the idea of normalization, in particular batch normalization, in a recent module, and definitely this helps. This is another very important tool in your disposal, but it won't fully solve the problem for a very big L as you increase deeper and deeper L. Like the deeper you have, the chances of you encountering a situation where the gradients get very small increases, and then you're out of luck as you get towards the layers closer and closer to the input. It's like flipping a coin at every layer and saying, am I going to get a norm much less than 1? And eventually you're going to end up with a situation which ends up forcing your gradients to 0, which ends up with a situation where you're not learning your parameters. So the idea is learning, I mean, this is a bit abstract. We haven't really talked about this too much, but the core problem, you can read about it in these papers, is that learning the identity function across many nonlinear layers can be challenging. So along comes ResNet. I should have cited the paper right away, but the paper will be in the references. So you have your familiar d-dimensional inputs x. This generalizes to every block. Okay, so we're going to have a bunch of blocks now. We're getting a bit more complicated than just plain neural networks now with CNNs. Soon enough, we're going to get into time-based models and recurrent neural networks, and again, we're going to see kind of architectures that are made up of a bunch of parts, which is getting kind of exciting to me. And then eventually it'll culminate with transformers. But we already have these blocks. So a block consists of a couple of things. It'll be a composite mapping of several things, and that block will be repeated over and over. The architecture will be repeated. The weights will change, obviously, but the structure will be the same. So this block here consists of our good old-fashioned linear regression, which we always need. This linear regression is passed through a batch normalization. This batch normalization is passed through our nonlinear activation function, sigma, which is usually ReLU. There's another weight. This is basically another linear operation we learn. And this is passed through another batch normalization. These weights are the weight matrices of our convolution layers. We defined convolution layers in the previous module, but they have basically a bunch of kernels that basically scan over the two-dimensional inputs. So X will be two-dimensional images or pseudo-images. We'll have kernels that move over them, or kernels/filters that move over them. And the nature of those kernels will be our convolution layers. So H is our block. And we're calling it H because it's kind of like a hidden layer, but it's not a hidden layer. So we want to use the same kind of terminology. But big H is not a single hidden layer. It's a sequence of a convolution here, batch normalization, nonlinear activation, another convolution, another batch normalization, and all of that together is our block, which we're calling H. So a little bit of a under the microscope thing. It's a bit more texty here, but be it as it may. Suppose our block that we have doesn't need to transform its inputs very much, so the optimal mapping will be close to the identity. So the block of X will basically return another image which is almost exactly X for some reason, arbitrarily to say it's for some reason. In a plain convolutional neural network, these blocks' parameters have to kind of conspire across these two convolution layers we have within our block and our nonlinearities to produce our output for all of our inputs. So any possible input, we're going to have these two convolutional layers intercepted with nonlinear activation functions that are going to have to work together in a way that we can't automatically have happen because we have a sequence, right? Like one thing leads to another in perfect series. And there's no kind of back channels by which these different actual layers can collude with one another. So, and not only are there no back channels, but there's all these other problems. So ReLU discards negative activations. You remember it's 0 up until 0, and then it's linear. And then the softmax basically follows a similar sort of pattern. So the composition of a sigmoid in a batch normalization in a weight matrix, all of this won't be invertible. Batch normalization recenters, rescales. It'll distort the signal, making it hard to learn this sort of relationship. The gradient flow through this chain will involve lots of products of these Jacobians, and every time we multiply Jacobians together, again, I mentioned this coin flipping metaphor, you risk shrinking, or also, on the other hand, saturating the gradient. Both are bad. And as you increase the depth, more and more of these overall complicated blocks, you have to keep on solving this problem independently, constantly. And any kind of errors are going to compound, and you're out of luck. So now suddenly we have this situation where we want to learn some particular possibility, and we're getting kind of squeezed out of that possibility by the nature of our complicated CNNs. I'm not actually distinguishing between complicated and complex, but it's certain that we have a vast series of layers growing now in our computational graph, going back to that concept. So the reframe from this paper, which I'm going to cite here before I post it, if I recall, is instead of asking the block to learn this function big H of x directly, we're going to have a residual. The residual is called f, and that is the difference between the block's output and the input. And now we can reconstruct the target based on this skip connection. So what we're trying to produce is going to be f of x plus x. Like by definition, this is what we're trying to predict. So we have y, we have h of x. If we have an optimal mapping that is close to the identity, then f of x should go to 0, and then we're left with y equals x, h of x is x. And then this will be achieved by driving some weights towards 0, the weights related to f of x. We're very happy. And then this, we talked about this in the context of L1 regularization. If we force a bunch of stuff to 0, this will make optimization a lot easier. We also saw it in the context of a dropout very briefly. Like forcing things to go to 0 makes learning a little bit easier in the remaining parameters we have at our disposal. So the residual block looks a little bit something like this. Here's our concept. The residual is our block's output minus its input. We defined this a second ago. We have a shortcut here. So here we have our convolution pass through. Sorry, there's something called Mermaid, which sometimes looks good on one computer and one browser, not in another situation. You should be able to just copy these out regardless, but I mean, it should be obvious anyway when I walk through. We have a convolution, and then we have the batch norm, then we have a ReLU, then we have a convolution, then a batch norm, and then this is h of x. Then we have x itself. This skips the line. This is, I'm not going to provide a metaphor here, but this is like the unfortunate, I mean, in real life, we wouldn't like people skipping the line, especially if we're, from Quebec or from England. Skipping the queue is a social faux pas. Anyways, all of this, the h of x and x will be passed in through a ReLU, which provides our outputs. So anyway, we have the skip identity, which allows us to basically combine h of x and x. If the optimal function is close to identity, if there's not much of a change, the network only has to force f of x to be equal to 0, which is super easy. And without skip connections, it has to learn h of x equals x, but like we complained about a moment ago, this can be hard for a number of reasons. So if we're going to have the skip connection, if now we have a neural network in which each of these are, weight matrices and other parameters we need to learn, and then we have the skip connection. So this skip connection has to be implemented in terms of vectors and weights and multiplications. It has to be implemented within the overall framework of the computational graph. We still need to push gradients back from the right towards the left when we're doing learning. So how is that going to be different? So consider a stack of big L residual blocks. We still have these somewhat complicated blocks, and we want to push gradients backwards. We have the output of block L is going to be the input at block L plus 1. So we call it X is the input at block L plus 1. This is just the input of block L plus the residual, the leftover of F of L. Remember, F is whatever's left over when we take the output minus the input. So here it is. We have X of L plus whatever's left over, the residual. If you unroll this all the way back to X sub 0, then you have X sub 0, and I mean, you can do this yourself, right? So this is a recurrent function. So start with big L, which is the inputs to your last layer. Well, this is going to be the input to layer big L minus 1 plus its residual, and keep on unrolling backwards. By definition, you're going to get the sum, and the sum is going to be X sub 0 plus the residual at layer script L to layer, the next layer, which we defined previously. So the gradient at block 0, the block closest to the input, because of the chain rule, maybe the chain. Whenever I see the chain rule, I'm kind of tempted to put the microscope here, but as you've seen by now, you're going to need to learn the chain rule, at least superficially. So we've seen a derivation of this before. Like the chain rule is basically the derivative of the loss of the prediction of whatever this overall network is predicting compared to the desired output. That's the loss or the empirical risk. Derivative with regards to the inputs. So pushing the gradients all the way back through the neural network to make updates to the weights closest to the input, and every weight along the way will be, just a product of all of these gradients. It's a product of the loss with regards to the output of the big L block times this. This function is the derivative of X sub big L with regards to the derivative, with regards to X sub 0, which we've just defined a moment ago to be this function over here. So the derivative of X sub 0 with regards to X sub 0 is just 1, so there that is. And then you take the derivative of this function with regards to X sub 0, which is, like, I'm simplifying things a little bit, so instead of having these arguments, they're kind of hidden here. Instead of having script L equals 0 to big L minus 1, that's all hidden here, but it's still the derivative of this big sum. So I'm just going to leave it there for now and not actually solve it, but that's what we have to do. I mean, to implement things fully, you have to go deeper, but again, I don't want to get too deep here. This is not an aside slide. But you can see what we're doing. Even with this residual connection that we've added, we know what the inputs of every block is going to be. We can unroll the whole neural network now. And we know that we're going to have to take the derivative of the loss with regards to the input at some point to push the gradients back. We talked about this at great length before. Before, we used the chain rule to multiply together a lot of we unrolled these derivatives so we could take this, the derivative of the loss with regards to the inputs in terms of these partial computations along the way. We can do the exact same thing. The only weirdness now is that we have this X sub 0 term added to this sum. But we know what to do with this. The derivative of this plus the derivative of that is this thing that we add to the derivative of big L times with regards to its input of that particular block. Hope that all makes sense. So this is nothing really fancy at all with regards to calculus, but it's more or less a repeat of what we talked about before, except we have this residual connection now. This one term, this identity term, ensures we have a direct gradient highway, essentially, from the loss all the way back to the early layers, which is nice. We can skip over a bunch of other layers and push gradients backwards. We can skip any kind of training stability. So if there's any kind of training instability in this little miniature sequence in this block, this is one big block here. If there are any instabilities here, vanishing gradients, exploding gradients, we still have this other path that can bypass things and push gradients backwards through the neural network to avoid those kinds of problems. So fantastic. This is one of the key insights here, and which is one of the reasons why this isn't an aside slide. Anti-example. So whenever we introduce a new idea in machine learning, people I think often are tempted to be like, well, this is the silver bullet that will be the final nail on the coffin of problems that we have to deal with. All you have to do now is apply residual connections and everything will be solved for us. And that's obviously not going to be the case. Imagine there's a student, not a student in this class, maybe some other class, that implements a 50 layer or 50 block ResNet. So there's 50 blocks in the ResNet. And they obtain 99% training accuracy and 60% test accuracy. And they'll conclude that ResNet solved their problem. 60% might appear to be good. But this is not always good. You always have to be curious and scratch the surface a little bit. ResNet seemed to fix the degradation problem. So we solved the problem of exploding and of a particular vanishing gradients in this very, very deep neural network. So training stability, that problem we talked about in previous modules, is helped, which is nice. And Linux will help me right now. Thank you, Linux. But overfitting is still a problem. So way back to the very most naive portions of this course, not naive, but earlier portions of this course, when you have, it's hard to tell what is overfitting from this like single sentence description of the problem, but we talked about before where we have very high training accuracy and relatively low test accuracy. This can mean that the model is not deploying well, it's not generalizing well. This is overfitting. So we still have overfitting. Even if we've solved some problems, other problems still exist. If training accuracy is high, and test accuracy is low, this is overfitting, but it's not exactly a depth problem. So we've gotten around some of the problems associated with depth and over flexibility, over too much capacity, but overfitting can still happen. I can kind of stress that enough. Overfitting will always be over your shoulder. So you can fix things. You can have more data if it's possible. You can still play around with regularization. So we have like batch norm, which sometimes is considered to be within the same family as regularization, but you still have dropout. You still have weight decay, other forms of regularization at your disposal. You can still augment your data with SMOUT, with ADASYN, if it's suitable, or with synthetic data. We're not going to see too much adversarial networks in this class, but you know that you can synthesize images within the context of computer vision. That can possibly help you bring this number up a bit. So here's just avoiding some common confusions with ResNets. Skip connections give you better optimization, so you can train deeper and deeper neural networks without falling into the traps that we've found laid out for us. But just because we have a new tool doesn't mean our other problems are solved. It's not a silver bullet. And you have to remember that overfitting and degradation are different failure problems with different diagnoses, and go back to the different modules in the past to remember that. So here's the paper that I could have cited before, but this paper, I'll probably cite it a few more times today, I think throughout the next 25 or so slides. They have different variants of ResNet. So when you say I'm using ResNet, normally you say I'm using ResNet 50 or ResNet 34 or ResNet whatever. I can say that I use an awful lot of ResNet 50 in my previous life. ResNet 50 has 50 like blocks of these convolutions and batch norms and nonlinear functions blocked together. The authors call this bottleneck, and there's about 25 million parameters in this case. It's kind of pre-trained, so this, in some sense, ResNets are foundation models. So you can grab a ResNet model from the internet and just download it and start using it right away without having to train from scratch. And I'll skip over a little bit of transfer learning here, but when you take a data trained on one set of data and retrain it a little bit to another task, starting with a good foundation, often serves you well. So ResNet 50, here's an interesting kind of little fact here. So ResNet 50 has like many more layers than ResNet 34, 16 or so, but it only has about 4 million more parameters. So the increase in parameterization isn't as big, and this is because of these bottleneck blocks that kind of helps us control the over-parameterization of a model. Even if you increase the depth, which we want to do to learn different layers of complexity in whatever we're looking at in terms of imaging, we can do so by still reining in the parameter counts a little bit through things called bottlenecks. So what are bottlenecks? Well, here's a bit of a comparison again. Apologies for Mermaid, this little module misbehaving here. But here we have the skip connections we basically saw before. We have like two 3x3 convolutions. So we have a little kernel filters that move across our images, and we can learn their parameters. So we have these little convolutional blocks, and they're the same width throughout. A bottleneck block will have more layers within these blocks, but they're going to kind of compress information through so-called bottlenecks. Specifically, they'll have these 1x1 channels. We'll still have a 3x3 process. So here in the middle is our 3x3 little kernel that has all the little benefits of convolutions that we talked about in the previous module. We still have our batch norms and our ReLUs, but we'll have our bottlenecks where we have these tiny little convolutions that we have to pass information through. And by forcing information to pass through these tiny little convolutions here, this basically does cheap channel bookkeeping. It's a little bit like PCA. It's a little bit like feature compression, and it'll help us retain information that's valuable. And the 3x3 convolutions will do all the spatial work that we talked about last time. So we'll still have this skip projection over here. This is another 1x1. So when the channel count changes, we're going to have to account for it also to make sure everything lines up properly. But this is handled for you under the hood. You just need to know that it exists. This is under the hood, certainly, but this is just for implementation's sake. And again, maybe if you get into graduate school or into machine learning science, this might come up again. When your spatial resolution halves, we talked last time about stride. You can jump over the image with your kernel, or if the channel count changes in some other way, x and the residual f of x will have different shapes, so you can't just add them together or subtract them. You can't just do arithmetic simply like that. You know that you can't add vectors of different sizes to each other, so that the idea is here. You can take a couple of hacks. You can do zero padding, which people sometimes do. You can pad x with zeros to match with the channels. You need no extra parameters. You just have to, you learn the parameters that matter. Set everything else to zero, but you can still add them. Add the x's, the padded x's and f of x. You can take projection shortcuts, so you can use a 1x1 convolution with a stride to resize x. So you can have this kind of funky function over here where you have the residual, which of x has its weights. You can also have this shortcut on x, and this combination you can set w sub s in such a way that you could add everything together. You can add your inputs here, x, and with the more complicated convolution blocks in a way that gives you your y's, your outputs. So there's lots of little hacks you can do to get everything to work. I mean, when I say hack, hack doesn't mean it's bad, it still works. So again, this paper found that projection shortcuts, option 2, can slightly outperform zero padding. But again, your mileage or your kilometerage may vary. Don't trust anyone, me, Hey et al., anyone else. You always want to do the experiments yourself. ResNet-50, that's the kind of the foundation model that I use a lot. It's super popular. It uses projections for what it's worth at downsampling layers only. But again, this is under the hood a little bit. I'm just saying the thing to get out of here is that when you're doing these kinds of modifications on components of your neural network, you just have to make sure that you can still add things together, that the things plug together properly by having the same lengths. So I'm going to take a moment here. This was a particularly complicated module for me to produce. Initially, I produced examples where I compared ResNets against simple neural networks, or I simplified CNNs to a point in which I was getting good performance on ResNets by comparison, because I wanted to mimic the kind of scenario you would more likely encounter in real life. In real life, if you had a ton of data and a ton of compute, when I say tons, I mean reasonable to the task, you're going to have you're going to see that indeed the situation I mentioned earlier with plain old CNN performing worse and worse as you get deeper and deeper. You'll observe that, and ResNet will be relatively stable, and ResNet will have better performance. So truly, I wouldn't waste my time by producing a module extolling the virtues of ResNet if it wasn't truly better than, in most situations, than just stacks of CNNs. But I did not want to do that because it felt like I was cheating in some sense by putting up a straw man, by putting up a baseline that was too easy to get performance that pedagogically would work. So I needed to have a good baseline to compare against ResNet. Unfortunately, like you're going to be downloading my code and running it somewhere, and on my laptop, and even on my AMD, which does a better job at CUDA than lots of NVIDIA cards do. It's very computationally expensive to have a big model to show you these differences. So what I'm left with now is something that is not a straw man baseline, so it's a relatively good baseline, but it's small. It's a small ResNet and it's a small CNN. So these differences I talked about, where the deeper and deeper you go, ResNets get better and better, it's not going to be really observed here. So I'm just going to warn you now that the results are still going to be fairly good, a big picture, but the main story, which is that ResNets solve this problem, are not going to be easily observed in these examples. So I want to make that really clear here. I did not want to set up a straw man because straw people are logical fallacies. So don't do it. And it felt like I was taking a shortcut here. I didn't want to do that either. But given computational constraints, it is what it is. So still, I think these are still interesting examples that demonstrate how to implement ResNets. So their value, for me anyway, hopefully for you too, far outweigh these caveats. So we want to see if a small ResNet-style neural network will actually train better than a plain CNN of a similar capacity. Okay, so we're going to go back to CFR10 with some sampling. It's not optional for us, but we're going to do a subsampling. So we're going to have a small training set, small validation set, just so that I could compile my slides, because everything is happening in my slides. Whenever you see Python, it's actually running, as I've mentioned several times, because I think it's super cool. We're going to have 6 to 8 convolutional layers, ReLU, and pooling, like we've talked about previously. And we'll have a small ResNet, a similar number of convolutional layers arranged in residual blocks. So we're just going to grab this. We're going to train for a small number of epochs, again, because of computational constraints. We'll track training and validation accuracy and loss versus epoch, like we've been doing, and look at parameter counts, and just compare how we're doing. So let's see, anything new here? I'm pushing things to CUDA if it's available. I'm grabbing a CFR10 somewhere. Here's where I'm grabbing it. And I'm grabbing train and test. Anything new? Nothing's new. I'm taking random splits. So I'm taking random split because it's at a torch, and I'm kind of doing a lot of torch stuff here. In the past, I think I've relied on sklearn a little bit. There's no real reason why I switched here from sklearn to torch. It's the same general idea. It's just a different function to do the same thing. So here's all my data, and just split it in terms of training size and validation size. And then load the data in for training, validation, and test. So I have 8,000 training data points, 2,000 validation, and 10,000 for testing. So again, this is not a normal scenario. It's just for explanation's sake. So we can train. I'm not going to go through every single block here, but it follows the same kind of approach. We have several blocks here. So these blocks are kind of just like visually separated by lines. But like I mentioned before, we have convolutions passed into batch norms, passed into ReLUs, patched into convolutions, passed into batch norms, passed into ReLUs, and so on. So we have a sequence, a series of these operations. No shortcuts. This is a plain CNN. And these are all just parameters that are kind of typical for CFR10. So we have 32 by 32, and that's basically it. We have our classifier at the end. Everything's defined like we've done before. We push our model to the device. We count the number of parameters we have using this little function, and that's it. So our plain CNN has about 290 or so thousand parameters. The residual block. So here is kind of implemented kind of from scratch here. We have our initialization. We have our, pardon me. We have our convolutions, batches, convolutions, and batches. We have our projections. So here's where we define the projections. Our projections are, again, convolutions and batch norms. And if there's no projections, we don't have any projection. There's no shortcut. Our identity is just the function x. Our output is going to be the convolution passed through the batch norm, passed through a ReLU, and then we have that ReLU is passed through another convolution and another batch norm. If we have a projection, then the projection is the identity, and we have the projection passed through the batch norm of the identity is our new identity. Our output is whatever the output was from the block. So again, this just defines a single block. And if we have projection, which we do, we're going to add our identity, that shortcut at the bottom, that skip connection, to whatever the output was. I don't need to do this, but I'll do it anyway. This add over here, this little plus, is what we're doing. I'll just here a moment ago. Here, with this little plus, we're adding our complicated block to the identity. This is passed through a ReLU, and this is the output of our basic block. This is the output of this entire block down here. So we're actually implementing a ResNet from scratch here. Let's make that clear. And then our small ResNet will consist of several blocks. So it'll be a sequence of a where am I? Convolution, batch norm, ReLU, and then here's our basic blocks. So here's our basic blocks, which are with our skip connections. Basic block, a basic block, at these different stages all the way to the end. So this is sort of a conflation of what we were doing previously. I don't want to spend too much time on this in this video because it's really getting into the details that I could talk to you in person about. Here we have our 32 by 32. This goes to 64 by 64, which goes to 128 by 128 in the sequence of these convolutions and batches and ReLUs. And here, when I'm defining my small ResNet, I still have my initial convolution, which goes to 32. I have my batch norm and ReLU, but here's where I go through my both three stages I mentioned a moment ago. I have my 32 by 32 blocks. This goes to 64 by 64, which goes to 128 by 128 through these pairs of blocks. I have a stride, and I will solve that with these what do you call them? The bottleneck blocks, which are implemented here and here. So I have my small ResNet, and then I have my my forward pass, which basically pushes everything through the stem, which is the initial input, and then through the three ResNet blocks, and then finally the pool, where I pass everything through the average pooling at the end, and then I flatten to do my output. So forward is a forward pass, as you remember. So I have my small ResNet, push it to my device if it exists. I can count my parameters. I have way more parameters. I have about 700,000 parameters now with my ResNet. Solving the parameterization wasn't the main task. It wasn't the main problem of doing ResNet connections. I was doing ResNet connections, remember, because I wanted to potentially skip over blocks if those blocks had problems with pushing gradients all the way through, right? So if some of these gradients go to 0, I wanted to bypass that problem, have a little special highway for me so I could push gradients down that highway and bypass those problems. So 10 more parameters that I have to learn, but I have this special new addition to my architecture, which hopefully will come in handy. So here's our training. This is a function that basically trains one epoch. Nothing new is happening now. I am pushing my data to my device. I'm zeroing out my gradients, as you have to do with PyTorch. Get my logits from a forward pass. I specify my criterion, which I did previously. Push things backwards, do an optimization step, compute my losses, get my predictions. Here's where I'm kind of tracking my performance. So how much do I get correct? Well, how often do my predictions match the true class? Sum them up, itemize them, put them in correct, and and this is just the size of it. So like this counts the total number of classification attempts I'm making. And return from one epoch the change in loss, proportional, and the change in my accuracy, proportional. I mean, change in accuracy. And then do my evals. So nothing new here either. So I've walked through everything already, so all good. So this is just my definitions. Here's where I run it. So when you end up running this experiment, this is where you're going to see you hanging. So hopefully you have access to CUDA, which will speed things up for you a little bit, but that's as maybe also. So I have more or less the same kind of experiment I've been doing before. I specify the number of epochs, specify my learning rate, push my model to my device, specify my criterion. This is a classification task, so I'm using my cross-entropy loss, which we defined previously. I'm going to use Atom, which I like quite a bit. It serves a lot of good purposes. Here's just my history, which I'm going to keep on updating as I keep on going through the epochs. And then through my epochs, I'm going to train one epoch at a time and evaluate and store everything in my history, and then eventually return my model that's finished training and in the history of training. Given that model, so anyway, that's my definition for running an experiment. I run an experiment with a plain CNN, 8 epochs, learning rate of 1 to the minus times 10 to the minus 3. My small ResNet, which I defined by hand, 8 epochs, learning rate is the same. So again, small ResNet is going to have a lot more parameters. Actually, here it is. It's about, well, it's about more than double the number of parameters, but it's the same number of layers as my plain CNN. It's just that I have a bunch of extra parameters I have to keep track of because of my bottlenecks and because of my skip connections. But I have the same number of blocks. So I have the same number of plain CNN blocks as I have of small ResNet blocks. So I'm trying to keep things as comparable as possible to compare apples to apples, so to speak. Anyway, I run the experiments, I keep my models, and I maintain my history. And here's where the caveats come into play. So my final validation accuracy for my plain CNN was 60%. My validation accuracy for my small ResNet's only 53% on the validation. I get a bit better on my training accuracy with a small ResNet than I do with plain CNN. I mean, I think the story here is a little bit mixed, right? So this increase in approximately 3% or so on training kind of suggests to me that the small ResNet actually is doing a better job of learning on the training data. It's not falling into the trap where it's not learning anything. So gradients are moving their way through these increasingly deep neural networks more effectively for the small ResNet than they are for the plain CNN, because the training accuracy is a little bit higher. And again, 3% sometimes means a lot, and in this case I'm deciding to interpret it as such. So I mean, it's doing what we wanted it to do. It's solving those problems with gradient vanishing. But it's doing so at the cost of validation, so it's 7% worse on validation. And we talked about these problems of good training performance and bad validation performance. We talked about that even in this module. That's one of the possible symptoms of overfitting. And indeed, the training, like the vanishing gradient, is one problem of training, which we have to solve. Overfitting is another, and we've solved one, but at the expense of the other. We've had now so many parameters, we have such a powerful model now, that we're back to looking at the problem of overfitting, which seems to be what's happening here. So I think this is kind of the best of all the possible worlds I was talking about before. ResNet is not going to solve all of our problems for us. It solves some problems, it introduces other problems. But we know how to deal with overfitting, right? So there's no regularization really happening here, apart from the batch norms. I'm just doing plain cross entropy. I'm not doing any regularization. I'm not doing any dropout. So I know how to solve overfitting, and you can go ahead and do that. This is just a visualization of what we were looking at before. So the blue and orange are the plain CNN stack of blocks, and the green and the red are my ResNet in green and red for training and validation respectively. And training is better for both my plain CNN baseline and my small ResNet, and it's better than validation, which is normal. The extent to which it's different, it might be a sign of overfitting, which it seems to be happening for both of our models, not just a small ResNet. So the small ResNet train here, so you can see it doing a bit better. So it's pulling away as I'm training, and like I stopped after only 80 epochs, again because of computational constraints. If you have the most powerful, I did this on my laptop, now it's on a desktop, but if you have the time and you want to do an experiment, run maybe 100 epochs, see what happens, see if this difference changes. I'm not sure if it will, but that's up to you to experiment with. We can see the validation seems to fluctuate a lot. So, sometimes if I just stopped after 7 epochs, I'd be telling you a different story about how much better ResNet is than the CNN stack, even on validation. But that doesn't seem to always be the case. So that would not be honest. So, you keep on pushing this forward over many epochs also and see what you get. Again, this is easy questions for you to think about and jot down in your notebook. Which model achieves better validation accuracy? Which model appears to be more stable? How do the parameter counts compare? Is the parameter count itself a confound in your experiment that you have to deal with? Do you have to add more and more blocks of your CNN until the parameterizations are the same, and see if that changes results? Is there any overfitting? I kind of answered that question, at least to my eye. Maybe you disagree with me. You can tell me why. So for multi-class image classification like CFR10, you want to choose a CNN architecture that trains reliably. There's no failures that are happening silently or non-silently, observably. You want to always, generalization is the name of the game, so performance and validation is still important. Having a reasonable compute footprint. Like, to be honest, like I'm complaining about the compute, it wasn't that bad, but like when I'm making these slides, I have to recompile them constantly, and so like for the purposes of the slides, I needed to keep things constrained. But if you have all the time in the world and you're not constantly recompiling slides, go ahead and do the deeper experiments. And this is a reasonable computational footprint. All the regular diagnostics come into play. So validation and test accuracy, precision recall F1, supporting diagnostics, so looking at the shape of the curves qualitatively matters. Parameter count matters, but also flop matters, so like the floating point operations, like how many operations you actually have to perform is something that is kind of under the hood. We'll talk about that kind of in a moment, but just mentioning it. So, ResNets, and especially deeper and deeper ResNets, as you increase the capacity, will only be useful if it trains stably, if it improves all of these metrics, and if the complexity is justified computationally. Like if you're in a company or if you're deploying these models, if you keep on multiplying the number of parameters you have, you're going to multiply your costs of running these models, and that's sometimes something you can't really necessarily justify easily. Worked example 2. So gradient flow. So the whole point of ResNets is to push gradient flows back through the neural network through these skip connections. So I want to see if we can see any kind of gradient flow differences between a plain CNN and a residual CNN built from the same blocks. So we're going to go ahead and just take a look. We're going to peek under the hood. So here's our deep ResNet. So it's going to be a sequence again of this kind of what we call the stem, the beginning, and then basic blocks, stacked one after the other for the number of blocks we have. So we're starting with now 6 blocks instead of 3. So the default is 6. So we're getting deeper and deeper into deeper and deeper ResNet models. And then we'll have another sequence with their adaptive pool towards the linear decision making of the output of our neural network. Again, nothing we haven't seen before. We slap on a head on the top of these CNNs in order to make our classifications. Our forward pass is going to be the stem, defined here, and then all of these ResNet blocks with all these skip connections, followed by a pooling, followed by this flattening, and that's our outputs. So here I'm actually going to do experiments with a deep plain CNN, so with 8 blocks, and then our deep ResNet with 8 blocks. So the same number of blocks, but ResNet is going to have these skip connections. Everything's going to happen on device. look at our parameters. Again, our ResNet, it has about twice as many parameters as the plain deep CNN, but the ResNet's also a bit more complicated because it has extra connections and these bottleneck layers as well. So we can measure gradient norms. There's a lot of code here, and I don't want to, and these modules are based on theory, so I don't want to get too locked up in code. The in-class time we have together for these modules is why we have this flipped model, so happy to walk through this step-by-step in person. So all we're doing now is measuring the grad norms. We have our model, we have our loader, we have our steps, and all we're doing here is measuring the grad norms as we're progressing through the sequence. So we can see all of our grad norms over here. I think we can visualize it here a bit more cleanly. This table and this image are essentially the same thing. We have our plain CNN grad norms. We have our ResNet grad norms. We have our layers, up to a certain point. We can get deeper and deeper with ResNet as you go towards the right over here. As you can see, so actually, again, caveats from before, the CNN, the plain CNN, actually behaves fairly well. So the normalized gradients are all nicely right in the middle between 0 and 1, indicating that we don't expect a vanishing gradient, nor do we expect an exploding gradient. So everything looks pretty good. By contrast, and again, I just wanted to be honest by including every possibility here, the grad norms for the ResNet end up actually getting quite large. They go to 1.7, 1.4, 1.2, and so on in the ResNet. But performance will overall stay more or less the same. So I want to look at the gradients in the plain CNN. Do they vanish? They kind of vanish here around layer 0, actually. So it's not exactly like they're not exactly perfect all the way through, but this 0.17 is close to 0.2, which is pretty nice. Certainly don't explode. Actually, I'm answering your questions for you. So look at these gradients. Do you see any hint of gradient vanishing or gradient explosion in either of these two models? If yes, which of those behaviors, and if so, in which of those two architectures? Is the gradients more balanced? Actually, so what we would like is the gradients to be closer to 1. You remember from the discussion on gradients being pushed through neural networks. So 1 is sort of that sweet spot for the norms of the gradients. Indeed, which of these two is closest to 1? Some of them are small or far from 1, but some of them are far from 1 in different directions. How is this going to connect? Remember we talked before about the derivative of the loss function with regards to the inputs x. And we defined that using the train rule as the derivatives of the loss with regards to the predictions y or y hat. And then you had this sort of little linear term of an identity plus the derivative of f with regards to inputs, where f is sort of this residual block output from our residual. So we have gradients being pushed through the network. Some of them go through the convolutional blocks. Some of them go through the skip connection. How does that theory connect to what we're observing here in practice? And why is the gradient norms close to 1 when we're using the residual and not when we're using the plain CNNs? None of these CNN grad norms are close to 1 with maybe one exception, and this is not much of an exception, compared to when we're using these skip connections. How does behavior change? Think about it a little bit, jot it down, and come with any questions you might have. So wrapping up this module, again, this is not really getting deep, but it's getting a bit broad. It's looking outside of this scope of this module. I wanted to talk about ResNets and what they were and why we were using them. Those are the key messages of today. But ResNets also form the architectural theoretical foundation for a lot of other related modules. There's a model called efficient net, which looks at compound scaling. So they looked at different ways you can scale a CNN. We looked at depth in terms of depth D, width in terms of the number of channels you have per layer. Remember you had the idea of width in CNNs. Come on, Linux. Nice. We have resolution, so like if you change the size of inputs from 32 by 32 to something much larger. And then you have all of these compound scaling rules. So if you have a depth, then you have the idea that you have some parameter alpha, which multiplies by itself according to this user-specified scaling coefficient. So like the more compute you have, the larger value of phi you're going to have. So whatever depth is some factor alpha raised to the 5th power. And width is some other factor beta raised to some 5th power and so on. Again, this is all beyond the scope of this class, but you know how problems compound. When you have massive gradients and you multiply those by massive gradients, then they tend to compound when you multiply them all together. Same idea here. And so these kinds of constraints will balance flops across these different axes. Anyway, this model, just very, very high level, kind of looked at computational, like just raw performance in terms of these factors, depth, width, resolution. If you want to compare a basic block against a bottleneck block, and maybe that's something to remember in this particular module is what is a bottleneck? And a bottleneck is just those little pink modules we saw previously where we had 1x1 convolutional layers to basically do projection down into a smaller number of dimensions. So comparing basic blocks against bottleneck blocks according to H, W, and C. We have the compounding complexity of H, W, and C. C is our channels, W is width, H is depth. I'm going to skip over some of these details here because it's not really too crucial, and you can read the paper anyways if you truly care about it. But the key message here is that if you're using a bottleneck block instead of basic blocks, and you have these reductions that are happening, then you end up having smaller factors of complexity as you think about the number of flops or floating point operations that you need to have to perform when you're looking at the bottleneck block versus the basic block. So the basic block will be an order of magnitude more computationally expensive than using the bottleneck block. So another reason to use the bottleneck block for efficiency's sake. So given the same spatial expressivity, using the same resolution, and having the other same kind of hyperparameters set appropriately, bottleneck block can increase your efficiency. It can be 5.9% the efficiency of the other. So indeed, this is why ResNet 50 is, you can have, I mentioned at the very beginning, 25 million parameters versus 21 million parameters for ResNet 34. You can get a ton more like blocks, many more layers, but without the increasing cost and complexity in the parameterization of those models. So we have the idea of a dense net. A dense net is an obvious, semi-obvious extension. So we identified that having this skip connection from inputs to outputs and computing residuals is a way to get around some problems of pushing gradients back through a neural network. And let's just take this idea further and do many more connections across much more of the network. There's this famous paper called DenseNet, which won a prize at CVPR, one of the main computer vision conferences. And the idea here is to connect every layer to every subsequent layer. So you have the input at layer L is this block which takes in as input, in some sense, x sub 0, x sub 1, x sub L, and so on. Visualized here. So these papers come from this, so these images come from this paper. This is a very extreme feature reuse, and the result is fewer parameters for similar accuracy. So you end up, these highways you end up drawing end up being empirically very useful. They come at the cost of higher memory, so you're going to have to keep all of these intermediate maps If you're just doing a sequence, you can sometimes throw things away and keep things out of memory. So you can kind of have a thin memory pipeline if you have fewer connections. But if you're having to store all of these hidden layers and keep on passing them forward through the neural network, you're going to have to keep more in memory. So memory cost increases. But this is kind of what it looks like. Here's our inputs. Here's our outputs. These different colored blocks are all ResNet blocks, again, of convolution, ReLUs, batch norms. And I have the output of my first block is passed to my input of my, the output of my red block goes as the input of my green block, but it also goes to input of my purple block and to the input of my yellow block and to the input of my brownish block and so on. Okay, so I keep on kind of, like as soon as I compute something in a block, I kind of pass it all the way down to all of the subsequent blocks to take as input. Here's a super zoomed out view of the same thing. You can take these dense blocks. You don't have to have dense blocks all the way through your neural network. You can have dense blocks of ResNet blocks. So each of these little circles over here represents these little blocks here, which can be ResNet blocks, or they can also be CNN blocks. In fact, I think here they're CNN blocks, if memory serves. So they're all densely connected, as you can see here. But then you kind of silo them off. You do a convolution and a pooling, like you normally do at the end of like the linear, linear transformations. And then you pass that result into another dense block. So this CNN block, its output is not passed through all of the CNN blocks all the way down. There's certain kinds of filters that keep these dense blocks more local. So you get some of the benefits, but you don't have to be crazy about it. Okay, so hopefully you get the idea here. Here there's 3 dense blocks, basically this diagram is repeated in each of these 3 dense blocks. And there's pooling layers, convolution layers, and then there's a linear layer, as always at the end, as a head to perform classification. This appears to be a horse. So the takeaway here is that residual connections are like one idea, and they're like a point technically on like a spectrum or a wide landscape of models that reuse previous computations and kind of skip them forward and jump over blocks in order to be used later. And when we're doing training, we have to push gradients down backwards through all of these little pipes. We push them, quickly through these skip connections, like this very massive connection over here. We can go straight from the output to the input. And we also can push the gradients through the hard way, through each layer, one by one, using all the techniques we talked about earlier in this class. So you see a bit general idea, but the sky's the limit in terms of the kinds of architectures we can invent with these similar kind of ideas at our disposal. So how do you diagnose some of these residual nets in practice, like ResNets, but also the others like EfficientNet and DenseNet? Well, we always want to make sure it's training well, so we want to check degradation. So we look at our training loss curves, and if you get deeper and deeper in our architecture, does the training suddenly get worse? And in the first image we showed at the beginning of this module, it was yes, but that was a cartoon example. We did worked example 1 with real data, and indeed we saw the same kind of performance emerge. Are there vanishing gradients? So do we see any like near zero norms, or norms that are like closer and closer to zero, especially in early layers? And if that's the case, that's an indication that gradients are vanishing. We don't like that. And we can observe that through per layer gradient norms, which we saw in example 2. Are we overfitting? Look at the training curves in loss, look at the validation curves in loss and accuracy. And then if it's the gap that's increasing or big, then that's overfitting, but probably a solution to overfitting is to regularize more. Are there any filters that are kind of dead? Like are we learning, or spending time learning things that are pointless? Then this is a failure. We need to maybe re-architect things. If we if we're learning and we're kind of increasing our parameters or increasing part of our model, but our validation loss is plateauing earlier than we'd expect, then we can try widening our capacity, maybe try bigger convolutional filters or more of them, have more and more blocks, give more capacity to a model if it seems to be saturating early or underfitting. So you have a lot of things that can go wrong. Now you know this, and before you started this course, and certainly like your peers who only know how to send prompts to LLMs, they are like you're increasingly a true machine learning person now that you're understanding all of these problems. So every training run, look at training and validation. Don't just look at accuracy, look at all of the other metrics available to you. Look at gradient norms, maybe not at every single layer, but you can sample if you have many layers. You don't have to sample every single one. You can look at a couple of them. And look at confusion matrices also to make sure like fundamentally the task is not being solved for one group and not another. I wanted to mention that we're going to get out of computer vision now. Like this is an introduction class to machine learning, so we're not going to spend a lot of time in vision. We're going to jump to language next, but there's an awful lot more in computer vision that we're not going to have time for. I wanted to just touch on it a little bit. So we mostly were dealing with classification. We had all of these blocks of CNNs and ResNets, and we had a layer on top that did classification for us in ways that we recognized going way back to logistic regression. And we know we can measure top 1, top 5 accuracy and so on. But there's a whole bunch of other things you can do with computer vision. I wanted to highlight mostly, medical imaging is complex in all kinds of ways. Depth estimation, basically, it's important for self-driving cars. So if you're a self-driving car, if those still exist now, and you're looking at an image from a camera, assuming you're using a camera, computer vision, and you see what looks like a car in front of you or a person, how far away is that person, right? Like the depth of that pixel that you're observing is going to be important for you to decide how much brake force you have to apply. So you want to see how far away, even you get a flat image, all the pixels, all the observations in the world are flattened on this two-dimensional image, and you have to kind of estimate the depth of those pixels in space. Super important. I did a lot of that myself also when I was doing like surgical computer vision. But I wanted to highlight semantic segmentation in particular. So I'll just click on this link for a second. Can I do this and just drag it over? There you go. So usually when you look at, maybe not so usual anymore, but you're going to see examples of something that looks like this, like an image that is kind of colored in like a children's coloring book with these regions. And you can kind of tell, okay, with these red regions over here look to be people, and way down in the distance, those are people over there. Over here in blue are regions that look like motorcycles. These gray bars over here look like they might be bollards or kind of like little poles. Anyway, you can explore this a little bit to your heart's content. But I just wanted to bring that out here. Oh, come on now. Come on, Linux. So segmentation is a whole other task when I'm not just looking at an image and trying to apply a label for that whole image. And a more complicated task is like multi-label classification. So that's where you're saying, well, this image doesn't only have a horse in it, but maybe it has a horse and a cow and a farmer. So it's not just one label you're putting out, but you're outputting several labels. That's a level of complexity we haven't dealt with in this class yet. Possibly in 3152 you'll get into that. So classification on one hand, but segmentation is the task which is very similar to what we saw a moment ago. We have an image, like you see here on the left over here. This comes from the UNet paper, which another architecture for representing CNNs that is used a lot in medical imaging. Famous paper here. I click on this. Yet another architecture based on CNNs. But we don't just care that there's a particular growth in this image, or if like you're looking at a CT scan and you're trying to identify where tumors are, you don't want to just say that there's a tumor somewhere in this image. The doctor might make use of that, but they're going to want to see where the model thinks the image is. So the model should basically trace out where it thinks the tumor is in the image. So whether it's a tumor, whether it's a fracture in a spine, like in a vertebra or otherwise, you want the model to take the image and actually draw out pixel by pixel the regions in which it thinks something that's identified is occurring. So that's what's happening over here. You can kind of see it draws out this boundary around this object, and it can kind of color in the inside of this image, a turquoise color. So it's not just classifying that something exists in this image, but it's saying the thing I'm looking for is specifically in this region. All kinds of good uses for this. I have tons of images that I can show you from the papers we've published from surgery that like identified organs or instruments. Instruments are very easy to detect in a surgical setting. Anyone can do it. Anyway, so this is yet another task for computer vision that we haven't really talked about. I wanted to just mention it. With classification, we know we have metrics like accuracy, precision, recall, and so on. This is not something where accuracy will really do. There's something called intersection over union, and there's many variants of this also, but it's basically looking at the predicted regions versus the ground truth of these regions. It's looking at the overlap of these regions. So again, I'm not going to talk about this too much. This is a topic for another time. But if the prediction and the truth overlap perfectly, like if my segmentation perfectly matches the true segmentation of the thing I'm looking for, then the intersection and the union will be exactly the same, and then this fraction will be 1, intersection over union is 1, I'm extremely happy. But if the intersection is a lot smaller, so like if I predicted something way over here and it doesn't overlap the truth at all, then the intersection will be 0, and the union of all of the pixels in my prediction and all of the pixels in my ground truth will be something non-zero, so my IOU will be 0. That's the worst possible case. And if I have a prediction where, well, some of my segmented area overlaps the truth, but I also have some pixels which are false positives and I have some pixels which are false negatives, those false positives and false negative pixels will count towards my union of all of those pixels, and I'll have some pixels that are kind of true positives, they overlap, and as count the number of pixels in each of these sets, whatever is overlapping will be a proper subset in this condition, so the IOU will be somewhere between 0 and 1 non-inclusive, and I can therefore describe the quality of my segmentation of the model. You read more about segmentation again in this paper. There's other approaches. This didn't come up properly, so there's another BibTeX item which I want to cite here. That'll show up in the slides online. UNet is here, and so on. So this is just to say that there's other approaches to computer vision that is not doing regression or classification, but is doing something related to both. And I wanted to just mention that so you don't think I didn't mention it. Just quick checks, as usual. Here's your quick checks for you to just answer some fairly easy questions, mostly. And here are some references for today. As always, thanks so much. See you next time.